Mathematical induction, like you said, is a form of proof, a different way to prove things. In geometry class, you did proofs, but that was a different kind of proof. And there's all kinds of things in math that we prove. Let me kind of explain the point, by the way. Because in math, you have these theorems, and you know they're always true. They only call it a theorem if they prove, mathematically, somehow, that it is always true, without exception. All right? It's not like that in science. Science, they have these theories, they test the theories, and they can run experiments and see evidence that it worked. And it can work for 100 years, and then all of a sudden they find that, oh wait, this doesn't work all the time. It's not actually a law that has no exceptions, okay? And that's just, that's the real world. And I'm not denigrating the way science does things. I'm saying it's different. In math, we try to prove things, and if we say it's true, we mean it is always true, and there's no exception to that, okay? Or in the theorem, it'll say when it doesn't hold, which is why you should read the conditions on the theorems you learn. Now, so mathematical induction really works on a certain kind of problem, the kind where, well, basically, mainly where you're talking about something that applies to all integers, and then this just does it for you. Look at this. And I think this example with the dominoes is a great example of the principle. So let's say you're trying to explain to a toddler how you know that just turning over the first domino will cause the last domino to be turned over. Now, you know the first domino is being turned over because you did that. How do you know what principle makes it so you know the last domino will be turned over? It's a simple principle that you know, unless of course you set it up wrong, that tipping over any domino will cause one after it to be tipped over. You pair those two things. The knowledge that the first one's getting tipped over, because you're going to do that, with the knowledge that any domino being tipped over tips over the next one, and you know they'll all fall down. And that's mathematical induction. And so that's how our proofs are going to look. Two parts. You prove that whatever proposition that you're trying to prove is true for the first case, and then you prove this. And this, when I first saw this, I didn't like the way they said it. This way. And if you read books, they'll quite often say, assuming it works for this. And you got to be careful about assuming things, right? And so I don't like that word. I probably will use it later on. But the point is, what you're really proving is that if it does hold for the kth integer, then it will hold for the k plus 1th integer. Okay, that's the relationship you're trying to prove. And you prove that, and you prove that it's true to start with, then you have it all. So, because if what I said is true, then it works for 1, and if you know it always works for the next one, then it works for 2. If it works for 2, it must work for the next one, so it works for 3. If it works for 3, it's going to work for 4, and you get all the integers that way. Okay, so that's the principle. Now let's put it to use. So, by the way, I keep forgetting to fix this. Change that to a 2. We're basically trying to prove that this formula on the right will give the correct sum for this sequence every single time. All right, that's our goal. On these, what I'm going to do is call this Sn every time, and it'll be easier. So Sn represents the sum of the first n terms of our series that we're talking about. All right. Now, this whole thing, by the way, is what we call Pn. Our proposition is that this formula works for all n. Okay, and we're trying to prove that Pn is true for any n. Now, we start by focusing on 1. So S1 will be the sum of the first term. And basically, you try to show that both sides equal. Well, that's easy. S1 is just a 3. It's just the first term. And then I use the formula to find the sum of the first term. You plug in 1. And that becomes 1 times 3, which is indeed 3. And listen to me, every single thing I'm writing down, I expect to have on your proofs. So show that it worked for the first one, then say that. Therefore, the proposition is true for n equals 1. So we say it that way. Or if you want to write it out, the proposition is true for n equals 1, you can write that. But this is how we say that. Okay? Next, I want to see what's called the inductive hypothesis. Every single one of these, I want to see this written out. what we're going to try to prove next. And that is that if sk equals k times k plus 2, k is just some variable, but we're saying if this formula would work for k, if the formula correctly sums up the first k terms, we're going to show that if that is true, then s of k plus 1 will be k plus 1 times k plus 1 plus 2, which is just what you get if you plug k plus 1 into the formula. Okay? One thing to catch here is we kind of need to use this to get this. And here's how we're going to start out. We need to come up with the sum of k plus 1, but not using that. Okay? Here, let me write it out, then I'll explain this. I'm saying this is just evidently true. That if you want to sum up k plus 1 terms of the series, you could sum up the first k terms and then add on the k plus 1 term. Here, watch this. So, that's the first term, second term, third term, all the way up to the k plus 1 term. So when I say this, I mean the sum of the first k plus 1 terms. This is the sum of the first k terms. And once again, this is just that sum plus the k plus 1 term, isn't it? So this is just, like I said, evidently true. That if you want to find this sum, it's simply that sum plus the extra term. And like I said, in this we need to use stuff that we know to be true. That's evidently true. But this we're presenting, the formula works there, so I'm going to use the formula for that sum. Then I can find the k plus 1 term. The rule is right here. So I plug k plus 1 in that rule, and it'll give me the k plus 1 term. So that's 2, parentheses, k plus 1, plus 1. Now, let me pause. Any questions about how we set this thing up? And before we proceed, let me say, we know that this will give us the sum of k plus 1, and we're going to show that this actually equals this. But what is this? This is what the formula over here gave us, right? And at this point, we don't know that this sum actually, this is the right formula to sum all this up. But we're going to, we'll prove that. So I'm saying we want to manipulate this until it matches this side. Okay? Now, first let's simplify this. That's k squared plus 2k. This is 2k plus 2 plus 1. Or in other words, the whole thing becomes k squared plus 4k plus 3. Okay? Now listen to me. One thing you could do, I'm going to try to prove that this equals this. We could really just simplify this, and if they match, then you could do it. But we're going to take the harder route, and we're going to try to only manipulate this and make this end up matching this, okay? Which means we're going to take this and factor it. I'll put this here. And so factor that, you get k plus 1 and k plus 3, don't you? Well, we're close, because you see, we have the k plus 1 factor. That's good. And this is going to seem kind of weird, frankly, because we're going to unsimplify this. Look, this up here is something plus 2. Well, I'm just going to take this and split the 3 into 1 plus 2. Because I'm trying to take this and manipulate it to match this. Well, I can put parentheses around the k plus 1 and not harm anything. There you go. It matches, right? So in other words, finding s of k plus 1 this way turned out to equal, write this down, the value for, the formula for s of k plus 1, I think I'll say it that way, from the formula. So in other words, starting with the knowledge that this works for the kth term, follows that it must be true that it works for the k plus 1 term, because algebra showed that. And so now it's just a matter of writing this up. So next you say, therefore, if the proposition held for the kth term, as you say, proposition true for k, for n equals k, or in other words, in our case, we're saying if the formula works for summing up the first k term, then we just showed that it worked for the k plus 1 term. In other words, k plus 1 is true. And we have it now. What we have is that we previously showed that the proposition holds for 1. Now we show that if it holds for k, it will hold for k plus 1. Put those together, and you know that this is true for all integers, which is what we're trying to prove. That original formula will hold no matter what in it. Because, once again, it holds for 1, and then if it holds for 1, it's going to hold for 2, but if it holds for 2, it's going to hold for 3, if it holds for 3, it's going to hold for 4, and this gives you all the rest of them. And therefore, it works for all of them. And if you read the book, their explanation, they'll be more verbose. They'll say, they'll pretty much put everything I said into one sentence. They'll say, since it works for 1, and since we proved that if it works for the kth term, pk, it works for pk plus 1, therefore, the principle of mathematical induction, the formula works for all integers. All right, we're done. Questions about that one? Good news is we're going to focus on one kind of problem. The book had like several different kinds of problems that we'd be proving. We're going to stick with just this one. So they're going to look the same, in other words. We're going to do the last one next. I think the second example they have there is the hardest one, so we'll save it for last. So find this one, and we're going to take the same approach. First, once again, we're summing up a series again. I'm going to call it Sn. And we're trying to prove this formula would be the correct formula to sum up that series. Now, first we find the sum of the first term. I think it would be a good idea to actually write out the series. So, if I plug in 1 into this formula, what do I get? Josh? If I plug in 1, if I plug in 2, I get... And then anybody? And so there you go. That's what the series actually looks like. And so S1 is 1 in this case, right? If I come over here and use the formula to find S1, inside the parentheses is 2, so the numerator is 2, so the sum is 1. So therefore, the principle and the proposition is true for n equals 1. Or P1 is true. That much, okay? And we state our inductive hypothesis. Be that if the formula holds for k, if this formula does give the correct sum of the series for k, then it will hold and be the correct formula for k plus 1. So plug k plus 1 into our formula. That's what we're trying to prove. And once again, we're going to start with the same premise that to find the sum of the first k plus 1 terms, we could simply find the sum of the first k terms and add on the k plus 1 term. All right? Once again, we're going to use this for the sum of the first k terms. And we'll plug k plus 1 into our formula here that gives us each term. So I'll just spell that out. 3 times k plus 1, and then minus 2. And once again, you want to keep your eye on the ball. We're trying to show that this that we just set up is going to end up equaling this, which is what the formula produces when you plug k plus 1 into it. Okay? Any questions so far? Well then, since our goal over here is really a single fraction over 2, we should probably make this a single fraction. So in other words, this part, you get 3k plus 3 minus 2, or well, really it's just 3k plus 1, right? Hold on, I didn't write that part right. So that simplifies to be 3k plus 1, but I need it written as a fraction, so it's really 6k plus 2 over 2. Okay? Now let me bring this down. So I'm going to simplify that numerator. It's 3k squared minus k. No, it's right here. No, look. Oh, no, this is 3k plus 3 minus 2 was 3k plus 1. So this became this, and then I doubled that for the numerator. Now we combine the fractions, and you get 3k squared and plus 5k plus 2. We need to factor that thing. Not bad, actually. Obviously, it's 3k and k to start each factor. And then it's either 1 and 2 or 2 and 1. Which way does it go? Let's see, 1 and 2. Actually, that gives you 6 and 1 is 7. It's actually the other way around. 2 and 1. Because then you get 3k and 2k is 5k. Now, look at this. We got a factor, and one of the factors matches. K plus 1 here matches k plus 1 here, so here, I'm going to put it here. We're close. And I'm trying to manipulate this so it looks like this. And this one has a minus 1 tacked on, so what I'm going to do, this is going to feel weird, is take the 2 and rewrite the 2 as 3 minus 1. And I can do that. 3 minus 1 does equal 2, obviously. But I did that because, once again, it had a minus 1 here, so I needed a minus 1 at the end. And then we're almost there. What's the last step? Now, these two, when you factor 3 out of them, can be rewritten as 3 times k plus 1, with a minus 1 tacked on after them still. And we're done. And once again, I would write that up. That the whole point was that now matches exactly what the formula would have produced for k plus 1. So we found s of k plus 1 starting with this approach, which shows that equaled exactly what the formula would have produced if you plug in k plus 1. This is right up what we proved. Therefore, if the proposition holds for k, the formula works for k, then it will work for k plus 1. Now, once again, now by the principle of mathematical induction, since we know the proposition holds for 1 and we know that this is true, therefore, it's true for all integers. That formula will work always. We know that. I'm not really circling that. There's not an answer in this. Our proof, there is no answer. It's just your proof is, everything. It was all about showing that the original statement was true. Okay? All right, one more. Start the same way. What is S1? 1/3, yeah. My ears are old. I heard someone say something. And then over here, you find the same answer using the formula. Plug in 1 there, plug in 1 there, and we get 1/3. So therefore, the formula works for 1. Now our inductive hypothesis is that if the formula works for K, then the formula will work for K plus 1. And once again, we start with the knowledge that to find the sum of the first K plus 1, it'd be sum of the first K plus the K plus 1 term. And listen, if we were going to spend time on this, we might get to the point where you could drop some of this off, but actually, we had this one day of notes, you have like 8 problems to do for homework, 7 because I'm going to ditch one. Write all this down a few times we're going to do it, every single little bit of work. What goes here? Yeah. What the formula gives for K, exactly. And this is going to be kind of weird. We have to use this, plug K plus 1 into this. Unplug K plus 1 term. So, plug K plus 1 in here, and you get 2 times K plus 1 minus 1, like so. And plug K plus 1 into the other factor. Everyone clear where everything came from? Now it's just a matter of getting through the algebra to show that this actually equals that. First of all, let's clean up those factors. This is 2k plus 2 minus 1 is actually just 2k plus 1. Another one is what? Okay. I'm going to bring down the other fraction. And we're going to combine these again. So I need to multiply this by 2k plus 3, top and bottom, so they both have the same denominator. Okay? And so now they both have the same denominator. I'm going to combine those to be single fractions with the same denominator. There's the common denominator. I'll have an answer. And I'm going to just simplify each of these. Here, when you multiply, you get 2k squared plus 3k. And then plus the other numerator, so plus 1. And when you factor that, it's actually about as easy as it gets, because you know it has to be 2k and k. And then to get a 1, you pretty much can only do 1 times 1. You can hardly fail at that factoring. Thomas, what do I do now? No. Almost the opposite. Cancel that. We're close. Let's clean it up. That over that now. And once again, you want to kind of keep your eye on the ball. Look at what you're trying to achieve. We're close because the numerator matches now, doesn't it? And this denominator has a plus 1 stuck out in the end, so I'm going to take the 3 and split it up into a 2 plus 1. I was trying to just get a plus 1s in there. And then the first part, though, I can factor a 2 out of. It's always going to feel weird because you're not used to unsimplifying things. Well, there you go. We took this, manipulated it, and made it match this. No, no, no. No, we're done. The fact that you're asking that question means you weren't looking at this. So the whole point was to work on this until it looked like that. Okay? Because once again, we're trying to show that starting with this, starting with the knowledge that the formula works for K, and work with only things we know, we find that the formula will work for K plus 1. Yeah. Yes. And so this is something we know, and it works out to equal this, which means this did work. We know the formula does work. We proved the formula does work. And so here, let's write it up, and we'll be done. So if, it's always the same. If the proposition works for K, it will work for K plus 1. That's what this was proving. And then once again, the first part paired with this part together proves the point. That's what we're going to add on by the principle of mathematical induction. That's what I could spell mathematical.